Hello, Nathan, are you here?
Hello, Professor.
Hey,
Yeah,
thank
yes,
you.
yeah, okay,
Yeah, thank you for your support. So, yeah, it's not difficult. So as soon as the speaker arrives, please make him co-host and
okay,
support him and make sure that the recording is ongoing all the time. And whenever you receive question, I mean, if the speaker does not, I mean, recognize some question is entered in the Zoom chat, you may notify him that there is a question in the Zoom chat or something like that. Okay.
okay,
Yeah, I will be moving to another room, or maybe I will come back. Okay,
okay.
see you
See
later.
you, see you.
교수님 안녕하세요. 옵스, 안 되죠?
안녕.
교수님,
한국말로 해도
아,
되나?
네네. 교수님, 인사는 제가 한국말로 드리겠습니다. 교수님 그 파티서펀트 리스트에 ESWIC 로고 보이시죠?
네.
예, 그 친구가 예탱인데 교수님 그 지원하려고 여기 계속 있을 거고요.
네.
그래서 혹시 그 테크니컬한 어려움이 있으시면은 이 친구한테 부탁하시면 되고 저는 이제 방을 옮겨 다닐 거라서 계속 있을지도 모르겠는데 혹시나 제가 계속 온라인에 있을 테니까 급한 일이
음,
생기면 저한테 바로 연락 주셔도 됩니다. So yeah,
음.
thanks. So please support Professor Har. So if something comes up as a question in the Zoom chat, maybe you can let him know. And
Okay.
okay. Um, and 교수님 그 유튜브에 올리는 거는 이미 안내를 받으셨죠?
유튜브에 올리는
예,
유튜브?
이게 예, 저희가 이거를 다 녹화를 하고
예,
유튜브에 올리기로
예, 예.
했는데 네,
오케이.
예,
예.
혹시나 해서 그 저희가 이
음,
부분은 에디트 아웃 할 거고 뒤에 유튜브에 올리기로 했습니다. 그래서 어,
예.
예. 그런데 이 사람들이 다 유튜브에 올라가는 걸 아니까 많이 이제
많이 안
어싱크로너스
돌아도 된다. 예, 예, 예.
예, 많이
예,
안 오실
괜찮아요.
텐데
예. 몇 명이 들어도 괜찮아요.
네,
예. 오케이.
예. 여기 보니까 충남대 김영신 교수님 나와 계시네. 김영신 교수님 안녕하세요.
아,
나와 계신가 보네. 예,
아직 안 들어올 수도 있으니까.
예, 예. 아무튼 저는
어쨌든,
교수님 계속 왔다 갔다 할 것 같습니다. 또
그래,
뵙겠습니다.
그래도 한국말로
네,
이렇게 또 안내해줘서 고마워. 수고가 많네.
네,
예,
감사합니다.
그러면 시작은 내가 알아서 하면 되나?
예, 저희가 세션째 업기로 해서 바로 짤막하게 소개해 주시고 예,
음.
시작해 주시면 예, 곧 뵙겠습니다.
예, 그래요.
예.
음. 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 Hello, can you hear me? So, Yeteng, can you hear me?
Yeah, yes, I can hear you.
Okay. Thank you. Okay, let me start education class. First, I'd like to introduce myself. I am Professor Sun Hoi-ha from Seoul National University, Korea. As you can see, then I'm providing this lecture in my office. Welcome, everyone. This class is about design methodology for low-power computer vision systems. Okay, here is the contents of this class lecture. First, I will give you a brief introduction of what will be covered in this lecture. And actually, this lecture consists of two parts. The first part is general techniques for software optimization of deep neural networks on a given embedded platforms. After overviewing general software optimization techniques, then I will give you the real story, how we could won some LPIRC competitions by applying those method optimization techniques in a systematic way. And also, I will introduce a technique how to parallelize CNN applications for given network, specifically NVIDIA Jackson platforms. And I will conclude. I'm interested in embedded machine learning subjects because DNNs are popularly used in embedded systems nowadays. Embedded systems usually have various constraints in terms of computation power, memory size, and also the application-wise, there are real-time constraints such as latency and or throughput. And more than one applications may run together in systems. Then we want to maximize all those kind of DNN applications while satisfying all constraints. And specifically, I will focus on CNNs because CNNs are popularly used for computer vision applications. They are important application class in embedded systems. So, as you know, the main CNN consists of several layers. Among them, convolution layers are most time-consuming, and so we want to accelerate the computation of convolution layers. So let's find out how much computation is needed for convolution layers. So on the bottom figure, like info feature map is convolved with n filters to produce n output pixels. For each output pixel is output of convolution operation of input feature map and one filter. So number of multiply and accumulate MAC operations is equal to like FH, FW, N, and K times C. So you can see that the number of MAC operations is huge, and also we need to read this filter weights from the off-chip DRAM, or we have to read the input feature map, and we need to store the output feature map to off-chip DRAM if on-chip memory is not big enough. Okay, so in this case, to reduce the memory access frequency, people usually maximize data reuse possibilities. So after reading N filters, then we usually want reuse these N filters to compute the convolution output for input feature map. Or the people may want to reuse input feature maps maximally by reading filters from the off-chip DRAMs to produce output pixels. Okay. So how to accelerate DNNs? So accelerate DNN usually accomplished by addressing the following issues. As I said a minute ago, so the off-chip DRAM access is very time-consuming. So we want to minimize accesses low-level memories by using memory hierarchy. So providing on-chip memory and providing some local buffers, stream buffers. And convolution operation itself can be parallelized. So how the convolution operations has consists of actually 6 nested loops, and these loops can be parallelized in various ways. So we have to decide how and at what level to parallelize the convolution operations. And also we can use approximation techniques because computer vision applications usually do not require precise, accurate computations. Instead, we can apply various approximation techniques, such as using low precision numbers or pruning of the networks. And also, some researchers are very interested in and also heavily worked on to exploit some sparsity with zeros because weights or feature maps are likely to have 0 operands. And those kind of like acceleration techniques can be categorized into 3 categories. The first one is we want to take hardware approach by designing hardware accelerator, or we can, if a hardware accelerator is given and then hardware system is given, then we can apply software optimization techniques. If we have a freedom to design our new neural architecture model, then we also want to find the good neural architecture model that is called the neural architecture search. But in this lecture, our focus is software optimization techniques and systematic methodologies, assuming that hardware platform is given and also network is given, network model is given. Okay. By the way, I uploaded this notes into the chatting window, so you can download these class notes from the chatting window. And also, if you have questions, please write down the question using the chatting window. Okay. Okay, so now let's review each software optimization technique, specifically exploiting the characteristics of DNA applications by approximations. So DNA is highly redundant in general. So reducing the redundancy saves memory space and computation requirement. So in this lecture, we will review the 3 key techniques. The first one is reducing the size of operands for storage and computation saving. That is also called quantizations. And we also want to reduce the number of operations for storage and computation saving. There are 2 techniques. One is low-length approximation, the other one is network pruning. So let's look at each technique one by one. So quantizations. So I list some references, and that actually overview the history of quantization methods, as well as like some new quantization method. So quantization method has 2 benefits. The first one is memory savings. So by reducing the number of bits to represent numbers, then we can save the memory. We try to minimize accuracy loss. And if hardware platform supports, then we also can reduce the computation overhead. So if hardware supports multiple 4-bit ALUs, then reducing the integer numbers into 4 bits are beneficial. But if not, then even though we quantize the numbers into 4 bits, then if ALU does not support 4-bit ALU, then we have to use 8-bit ALU. Then maybe reducing the bits less than 8-bit may not be helpful in terms of computation time. So how many bits to use to represent numbers depends on the hardware platforms. So whether the hardware platform supports or not, we have to consider. So this is widely used slides borrowed from this paper image source over here. Then instead of using 16-bit floating point, if we use 8-bit integer, then we can save 1/10 of energy. So as well as huge drastic improvement of area. Okay. So people try to reduce number of bits for representing some numbers. So when we train the CNNs, deep neural networks, usually 16-bit floating point is used, or in actually GPU, or if we are using some server and cluster, we use 32-bit floating point. But instead of using 32-bit floating point, people want to use 16-bit floating point to reduce the storage space and also computation time. So have precision is widely used for embedded AI platforms, such as Jackson board. They support 16-bit floating point GPUs. So, and also Google TPU, for training, they support 16-bit floating point. The 16-bit floating point here, if we this slide shows you the difference, format difference between IEEE floating point format and bfloat, brain plane floating point format. If we compare these two formats, IEEE floating point format focusing on accuracy by sacrificing the dynamic range. On the other hand, this bfloat actually focusing on the range and sacrificing the accuracy, some precisions. Okay, and so people usually use bfloat to train the CNNs, to train the deep neural networks. And also some companies try to reduce the bit width further. So a proprietary 8-bit floating point is investigated. And Google TPU uses 8-bit for integer for inference and floating point 16-bit for training. So so we can use floating points, although for floating point 16-bit floating point, or when we use GPUs, but people are not satisfied with that results. So people try to use fixed point, so integer data path, to use an integer data path. So fixed point, it's a data path. They actually try to reduce the number of bits. So as shown below here, so original weight distribution, or that distribution comes from the floating point 32-bit. Then if we use some integer format, then actually we have to sample it, and we here linear this linear quantizations. Now we have to quantize those bits. Then the problem in this case, the problem here is how many, so the range. So in this case, how many bits we will use, and what is the maximum range we can represent. So parameter, the range of the numbers, integer numbers, is defined by minus max and plus max and number of bits. Then how to determine the max? Then among these observed values, we can choose real min and real max. Then that is one solution, min max solutions. But instead of using min max, then maybe we can use other ways. For example, NVIDIA solution is to minimize KL divergence to minimize these errors between observed numbers, quantized numbers, and real numbers. We measure the error to minimize it. And we can classify quantization techniques into according to various metrics. The first one here, I will say that like quantization of can be symmetric or asymmetric. So the symmetric quantizations is used in NVIDIA TensorRT. Also in TensorRT case, then they actually define some threshold value, and that 2 minus threshold and plus threshold are the same, and they perform linear quantizations. But Google actually use asymmetric quantizations. So as shown in this figure, that plus threshold is larger, bigger than the minus threshold, and then it actually is equivalent to moving zero positions to make a balance here. Then how can we define this minus and plus threshold? Actually is determined by looking at the real distribution of the floating point values. And this slide shows how we can compute, we can quantize this symmetric symmetrically distributed numbers shown below in the figure. Okay. And another classification is done by whether the quantization is uniform or non-uniform. So uniform quantization is popularly used, and it is well known that 8-bit uniform quantization works well in most cases. So this is the leftmost column shows the CNNs, and this table shows what is the top 1 and top 5 accuracy using floating point 32 and integer point 32. And below part, actually, we can observe the difference. As you can see, the difference is negligible, right? So 8-bit integer is just powerful, or that is sufficient. Using 8-bit is sufficient to preserve the accuracy of the network models. That is why almost all some CNN accelerators use 8-bit integer data path instead of 16-bit floating point or 32-bit floating point. And also TPU also use 8-bit integer data path, as I said earlier. Okay. So here are some example of nonlinear quantization methods here. The people have investigated the use of low quantizations. The low quantization means that the benefit of low quantization is we can use shift instead of multiplications. So, right, the shift means some exponentiation of the numbers. So if we use low quantizations, then we can use shift operations for multiplications. But this is actually the low quantizations focusing on small numbers, and the accuracy error grows as the numbers increases. So that is counterintuitive. So maybe small numbers have literally impact on the MAC operations, multiply and accumulate operations, then that result usually heavily depends on the large numbers, not small numbers, but low quantization does not utilize that fact. So people try to use low quantizations in multiple levels, and 2 levels and second levels. So they actually use different ranges of numbers, and we apply low quantization to level by level to reduce the error. Okay. And weighted quantizations, actually they determine, they actually cluster this weight, and they use different quantization level between these numbers. And also some researchers introduce outlier quantizations. In this figure says, like, if the number is small, then they use uniform quantizations, and they define some threshold. If the number actually is bigger than threshold, they use floating point formats, like 16-bit floating point formats. So they do not quantize outliers, and they use linear quantizations for small numbers. And they argue that this percentage of outlier is less than 5% or like 3%. And these outlier quantizations can save memory space quite drastically by using like 4-bit integers for small numbers. And for big numbers, they use 16-bit floating point, for example. That is beneficial by using 8-bit whole 8-bit integers in terms of storage. And it is a special case of mixed precision quantizations, and also it should be supported by hardwares, but maybe MPU does not support that one, so then this one is no help. And runnable quantization also is proposed, that is to determine these quantization levels during the training. So quantizer itself is jointly trained with model parameters to minimize the errors. So that is also a possible approach. Okay. And the next category depends on the quantization granularity. So quantization. So when we quantize, we have to determine min-max, minimum value and maximum value to represent numbers. That min-max numbers may depend on the layers, right? And also maybe depend on the channels. So layer-wise quantization means that this clipping range is common to all channels in each layer. And it is very simple and suitable for designing accelerators. So if you are using some accelerators, then, and instead of using different quantizations for each filters, they use same quantization layers for all filters. And the channel-wise quantizations is popularly used for CPU and GPU. So in this case, channel-wise quantizations, they use different filters have different ranges, right? Different filters have different min-max ranges. So by doing so, then they surely increase the accuracy by using layer-wise quantizations. And there is a trade-off. Group-wise quantization is kind of compromise. So group multiple channels to use this calculate the clipping range. So and sub-channel-wise quantization is also thinkable, but it is not really used in real implementations. So in summary, CPU and GPU target channel-wise quantization is popularly used because it actually can improve the accuracy. But if we use accelerators, then the layer-wise quantization is preferred. Okay. And so after determining the number of bits, then when we quantize numbers, we can use two methods. The first one is QAT, quantization aware training, and the other one is PTQ, post-training quantizations. So QAT it's the natural way of quantizing, the intuitive way of quantizing the numbers. So they so to quantize the weights, we have to determine min max. So we actually training the network in floating point numbers, and based on the values of the weights, then they quantize weights, and they train again. They train again, and they actually obtain the quantized numbers. After quantizing, they train again by repeating this process. Then finally, actually, they can get good performance, good accuracy numbers, because we actually retrain the whole networks. But this retraining is very costly. So recently, people try to quantize after training. So instead of training using the whole data set for training, they actually use some calibration data sets. So they use calibration data and they quantize the weight. So to quantize the key issue is that, as I said again and again, so we have to determine the quantization range. And so the simple one is min-max method, and the other one is like mean square error method. And also cross entropy can be used to measure the difference between quantized and unquantized. And they actually using calibration data, they try determine the quantization range and quantized models. And also this post-training, it's a simple, just naive post-training quantization lose accuracy significantly. So people actually improve these post-training quantizations by providing using various techniques, cross-layer equalizations. So as I said, like, so if the number range is quite different between layers, then they actually move some weights from first layer to second layer to balance the range of values. So if the weight distribution is too small, I mean the maximum number is too small for one layer and the other one layer, the numbers are large, then we just move some weights, scales, so balance between layers. So cross-layer equalizations, if they numbers are biased, then actually we observe the bias corrections. And also they found out that in the quantization process, some typical rounding is not good because it is skewed. It may accumulate the errors. So they actually use other round techniques. The rounding to the nearest is not optimal, they found out. So the various techniques are used in the PTQ. By doing so, they could improve the accuracy. And when we perform quantizations, one way, the more popular way is to simulate the quantizations. So that is processes known as fake quantizations. So even though numbers, we actually use integers, but inside the computation is done in floating point arithmetics. So it is not exact quantized computations, integer computations. For example, if we use mag operations, multiply and accumulate these filtering operations, the number might be too big, so we may use the reduced number of bits if we use integer arithmetics. But in floating point arithmetics, then we don't need to do it because the number we can have a large dynamic range. So the difference and the results might be different between fake quantization and real quantizations. So to faithfully estimating the accuracy, then integer-only quantization should be used, should be emulated in the floating point processing element. But that is another issue we consider. And recently, people are looking at using mixed precision quantizations. So instead of using same number of bits for whole layers, then they actually use different layers. For example, they use 8-bit quantizations for early layers, or they use reduced numbers 4-bit quantizations for later layers. By doing so, then we can actually increase. We can reduce the number of bits more without sacrificing accuracy. But mixed precision quantization is quite hot topic nowadays, and search space is really huge because it is basically exponentially growing as the number of layers increases, and we need to reduce the search space to use mixed precision quantizations. And another issue is that, like, if some hardware platform is really weak, like for IoT devices, for example, sensor devices, then people want to use like binary or ternary quantizations for low-end IoT devices. Then instead of using multiplication logics, they just use bitwise arithmetic for reducing the hardware logic drastically. Right, but it is surely it is useful, and there are a bunch of research results published in these directions. Okay, let me summarize the trend and current status and trend of quantizations. So nowadays, hardware-aware mixed precision quantization is widely researched nowadays. Actually, I am emphasizing we need to consider hardware limitations. So maybe 4-bit or 8-bit data paths are popularly used now, recent in processing elements. Then we don't need to quantize numbers with 6 bits, for example, because anyhow we will use 8-bit data path, right? So instead of using 6-bit data path, people try to use 4-bit and 8-bit and a mixture of these two to get the same accuracy. But actually, we can gain much by doing so. And nowadays, people they try to use PTQ method, post-training quantizations, to avoid the cost of retraining. But PTQ is successful for some networks only, image classification networks, and but we actually need to enlarge the application domain of PTQ method for segmentations and object detections and some more complicated networks. And also, on-device, low-precision on-device training may be necessary. And also, people are looking at zero-shot quantizations. If there is no training data, then we actually need to synthesize the data similar to training real data. Then by doing so, then you can still perform quantizations. Okay, So any questions on the quantization issues? Then let's move on to the next techniques, that is pruning. So here is also some survey papers, recent survey papers about pruning of the networks. So this diagram shows that how many papers are published in the major AI conferences. As you can see, these models, also pruning, also called sparsifications. Sparsification papers are growing year by year. So it means that pruning is very important techniques and very useful techniques too. Okay. So issues on network pruning. So there are 4 issues: what to prune, and which to prune, and how to prune, and how much to prune. Especially, so for given network, we may want to determine the pruning ratio. Okay, I try to reduce this network by half, like, or 70%. So if we determine the pruning ratio beforehand, then to achieve that goal, then we have to find out how to prune. So, and we have to determine all these ratios, and or we can define some kind of tolerable accuracy loss, and we try to maximize pruning ratio. So optimally searching for pruning ratio, that is another directions. So how much to prune? Actually, that is these two belongs to these answers belongs to these questions, these issues. Okay, what to prune? So what to prune? So sparsity structure is classified into 2 types. One is irregular pruning, or regular pruning, or unstructured pruning, and structural pruning. So irregular pruning is also called fine-grained pruning. So the pruning means that so after obtaining these weights, and by looking at these weights, if the weight is too small, then actually we make that weight to 0, right? That is by reducing by making very small weights into 0, that end up with this fine-grained pruning, like irregular pruning. But actually, irregular pruning is not helpful to reduce the computation time, because CPU, GPU, and any hardware elements actually does not ignore zeros of the data in the hardware itself. So usually regular pruning or structural pruning is used for software optimizations. So we can use this diagram shows that, like, we can reduce the number of channels. For given channels, we can reduce numbers, or we can reduce the number of rows or number of columns, or you can use number of filters. So this filter pruning. So CNN usually have many filters. Each layer consists of many filters. The filter pruning is preferred. So unstructured pruning was proposed by Songhan MIT professors, and he's like some famous paper, some deep compressions. Then there, the full networks actually, they're based on the weights. They can remove these links to make this sparse, and prune the synapses if the weight is negligible. By doing so, they can reduce number of weights in memory, drastically for VGG16 and RxNet pruning ratio itself. But as I said, it does not mean that we get such benefit, such gain in computation time. But anyhow, we can reduce our memory size by pruning. Unstructured pruning is still helpful to reduce the memory size and also energy, but it may not necessarily mean this computation time saving. So the other extreme is structural filter pruning. So if you look at this diagram, then this graph, so but if we remove this yellow filter, then the outputs, if you look at the output, then it remove one channel of outputs. So if we remove filters in the previous layer, then it corresponds to remove one filter at the output feature maps. Okay. Then how we can determine which filter to prune? So there are n filters, then which to prune, and so which filter to prune, that is another pruning criteria. That is issue of pruning criteria. So the most popular way and easy way is weight magnitude using L1 norm. The most popularly used is L1 norm. That is just add this magnitude of each weight. Just average magnitude of kernel weights. So based on that average values, then prune the filters. If the this average magnitude is smallest, then we can prune. And also, if we have to determine how many filters to prune, then we have to choose threshold. So if the average magnitude is less than this threshold, then we'll prune the filters. And similarly, L2 norm is also used. So in this case, so if we determine the threshold, after pruning the 70% of the filters, so if we find out its average values, then we determine the threshold and prune. So after pruning 70% of the layers, then we retrain the pruned network with 3 epochs. Then we can recover accuracy. From quite drastically. Okay, and actually this which filter to prune, people think that data-free methods of L1 norm and L2 norm is too ad hoc. I mean, so we may consider statistical sensitivity with the training data, and also we actually based on training loss functions. So for example, so prune the weights that have changed least, and we just check variations of the weight variations, for example. So there are various ways of some data-driven criteria proposed. And for example, data-driven pruning example is that so they actually determine the layer sensitivity. So some layers are more sensitive to filter pruning. So determine the number of filters to prune for each layer based on their sensitivity to pruning. So it means that the pruning threshold depends on the layers, not the same. Okay. So by doing so, we actually determine the pruning ratio for each layer differently. But for each layer, then we can use simply using L1 norm. Okay. And the last issue of the pruning is how to prune. Pruning schedule. The sparsify after training. That is the typical way. Train, then specify. And it can be done only one shot. So we train, and based on the weights, then we specify it, and that's it. We retraining. Or we can process this this pruning and retraining iteratively. So by doing so, we can minimize accuracy loss while reducing the network model itself. And differently from this training and specify, this second technique is specified during training. So during training by epoch, so we actually proceed with the epochs. So after, for example, 30 epoch training, then we prune the network, and 30 epoch training, another we train, prune the networks, and another. And so weights is not the final weights, but the weights obtained in the middle of the training by pruning them. By doing so, then we may obtain the pruned networks for single training. By how many epochs we will consider and how to prune, and that differentiate each method. But anyhow, the concept is like this. And recently people have investigated the third one, the prune the network first for given networks, and prune the network first and training, and it allows regrowth, maybe regrowth. But the point is that actually we the starting point is not the full networks, but we start with the pruning networks and add these models, increase the models. So net adapt is automatic pruning framework that is used to design mobile FV3. Mobile FV3 paper says that they actually use net adapt to prune the networks to reduce the size, and it actually determined the number of filters to prune per layer differently. So, and the pruning criteria was L2 norm, and they actually could achieve better results than mobile FV1. The mobile FV3 actually use this framework. And as I said, some pruning at initialization, or PAI. So pruning at initialization is hot topic for pruning research. So motivation is cheaper and simpler pruning, because it eliminates the need for both pre-training or retraining, and they assumes, but so far they assumes unstructured pruning only. So pioneering works, there are two pioneering works. The first one is lottery ticket hypothesis, that got the best paper award in ICAR 2019. So what is hypothesis? Hypothesis says that a dense network and randomly initialized network contains some subnetworks. So that subnetwork is called winning tickets. And if the subnetworks are somehow obtained and we train in isolations and with randomly initialized networks isolation, then we can reach the task accuracy comparable to the original networks. That means that there exists some subnetworks. So we can prune the network from the beginning, and we training that one. So that actually is a theoretical background for this sparse training. So somehow, how to obtain these winning tickets, how to get this sub network. So that is the research issues. So they actually prove this kind of hypothesis. They actually not prove. Actually, they show several cases to confirm the hypothesis, and that hypothesis is confirmed with some class of networks. Then people try to find the good way of find the winning tickets. And SNP paper is presented at the same conference, ICLR 2019. Then they actually suggest some pruning method. They just based on connection sensitivities, based on connections, they just identify structurally important connections in the networks. For example, or node is connected to is affect many nodes, then that node should be preserved. And they actually connection sensitivities they propose. So follow-up studies have been made after LTH, lottery ticket hypothesis, and SLEEP SLEEP paper was published. Specifically, in particular, lottery ticket hypothesis have many follow-up works. And so here is a summary of trend and status of pruning work. So which one is better? So training a large network and the prune, or we found out the small networks or good small networks. So if the pruning works, maybe we can design large networks and then we prune the network. That is what actually these pruning techniques do. But PAI says that if we find the good small networks, then we train it, then we can get the large networks. But what if then we actually have some small networks, but good networks somehow, good networks, and that might be better than training the large network and prune. So in fact, the training process is really important, and training techniques actually can increase the accuracy. That is well-known fact. And also more work to do. That is my personal view. Then we actually need to consider hardware platforms for pruning, hardware platforms for pruning, and we have to consider memory requirement, energy consumptions, and accuracy all together as an objective of the pruning. And also, recently transformer-based models appeared, and transformer-based models the pruning is a very effective way of reducing the complexity and reducing the size, memory space for transformer-based models. So that is widely, there's a very extensively researched nowadays. And the question is, pruning at initialization, catch up the performance of the pruning after training in terms of accuracy. That actually is the question to be answered. And this pruning and quantization and long coding, like that is combined together and to achieve a huge gain in memory space and also gain some speed up for AlexNet and VG16. That this paper is so famous, then I think you may have already known. So I believe, I think, so this is like a very famous paper and it's called decompressions. It is merger of pruning and quantizations. In this case, they perform pruning first and they apply quantizations. And later on, they perform some Hoffman encodings. Okay. So any questions on these pruning issues? The third technique, software optimization technique, is low rank approximations. Low rank approximations includes three these sub techniques: matrix factorization, Tucker decomposition, and depth-wise separable convolutions. These are all popularly used in current networks. So what is matrix factorizations? So matrix factorization says that a large filter can be approximated by a series of small filters. So in all AlexNets and have large filters, like 5x filters, 7x7 filters, or something like that. But the new models reduce this filter size. For example, Google LUNET used 5 times 1 filter or 1 times 5 filter in series to approximate this 5 times 5 filters. If you apply 5x1 filter and 1x5 filters, then actually applying these two filters consider all 25 pixels, same size of pixels are considered if we use these two filters. So number of weights here, the original number of weights is 25, but if we use 5x1 filters and 1x5 filters, number of weights is reduced to 10. So we can save the memory, and also we can save the time. And VGG16 and other recent networks, they usually use a 3x3 filter. So if we use two 3x3 filters, then the same number of pixels are considered. They actually considered to get also a feature. To extract a feature, we look at the same amount of pixels, same number of pixels. That is matrix factorizations. So 5x5 filter can be approximated by a series of two 5x1 filter and 1x5 filter, or two 3x3 filters. That is matrix factorizations. And what is Tucker decompositions? Tucker decomposition is that we reduced the input and output feature maps channels by applying 1x1 convolutions. So in this case, so if we have to we convolve with 3x3 by CI input channel filters and n of these filters to obtain this is output feature maps. But Tucker decomposition says then we actually reduce the number of channels to CI to CI dash, and we actually perform 3x3 convolutions and produce C0 dash channels, and we actually expand the number of channels by applying 1x1. So that is Tucker decompositions. So in this case, then the issue is that how to determine the C1 CI dash and CO dash. So number of input channel reduction ratio and output channel expansion ratio, we have to determine it. So if use, for example, if we use half of them, if we reduce the number of channels by half, then we can save the computation time by 40%. So huge percent, 40% is not small, right? A large gain can be applied. And this composition is widely used already in the bottleneck architectures. If you look at the LesNet or SqueezeNet, and they actually reduce the channels size. The input channel is 256. Then using the bottleneck architecture 1x1 filters, they use reduce the number of channels to 64, and they expand number of output channels to 256 by using 1x1. So this Tucker decomposition is already used in recent networks to reduce the complexity while maintaining the accuracy. The third one, the mobile net, depth-wise separable convolution, is also can be considered as a low-rank approximations. Some 3x3 convolution is can be approximated by 3x3 depth-wise convolution times 1x1 convolution. So in this case, by 3x3 depth-wise convolutions, they actually consider the spatial relationship between pixels, and 1x1 convolutions merge this channel by channel relationship between interchannel relationship and interpixel relationship are considered. They actually separate the relationship between pixels to find out features. By these stepwise separable convolutions are devised by Google in the mobile net series, and it is nowadays maybe de facto design of filters because the complexity reduction is huge. Complexity reduction is 1/8 or 1/9. So this mobile net or depth-wise separable convolution is widely used. Okay. So low-rank approximation is nowadays already considered, already exploited in the recent networks. But if some network use some large filters, then we can approximate the large filters with the small filters to reduce the complexity, to reduce the computation time. Okay, so this is the first part of this lecture. So we overview 3 key software optimization techniques: quantization, pruning, and low-rank approximations. They are both quite useful and popularly used to reduce networks. But the next one, the second part of my presentation, my lecture, how to apply those techniques systematically to get the most benefits. The most benefit by using those kind of techniques. Before moving forward, so any questions? If you have any questions, then I will answer. Okay, then let's go on. So the subtitle says that we actually won the first prize in low power image recognition challenge in year 2017 and 2018. So I will explain how we won this challenge as a case study, and I hope this will help you to optimize the software in if a hardware platform is given and application, the model, the learning application is given. Okay, let me explain what is LPIRC competitions. So at that time, the challenge's name is LPIRC, Low Power Image Recognition Challenge. So the problem is that we are given 20,000 images, and we have to find out objects, as many objects as possible within 10 minutes. But we also consider energy in our metrics. So the score is MAP over energy consumptions, accuracy over energy. And if we cannot finish, we cannot treat this 20,000 images, then we get penalty. So if I can finish 10,000 images, then the score is doubled. Okay, so the real-time constraint is really important. Really important. So real-time constraint, actually, the score is kind of find the sum matrix to consider the trade-off between accuracy, speed, and energy consumptions. The data set is ImageNet data set, and this is a summary of the winner results. So winner results, we improved this score by more than twice than the previous years. And again, we obtained more than twice. The improvement ratio is quite consistent, right? It's similar year by year. But, okay. So frankly speaking, we were not experts in this field, in this one. So at that time, we are kind of beginners, like maybe like you. So we did not know much about software optimization techniques. So when challenge was announced, then actually we started learn the existing techniques. Okay, and we actually examine which hardware platforms are available and which network models to use, because the challenge did not put any restriction on the platforms and network models. We can choose any hardware platforms. We can choose any networks. We have freedom. So the first step is to select hardware platforms and networks. Okay, so problem with object detections. Then which object detection net models we will use, we have to determine. And hardware platforms. So which hardware platforms we use, we have to determine. And after that, then we actually apply the software optimization techniques. So in this summary, as summarized in this table, we apply the pipelining, we apply Tucker decompositions, we actually use quantizations, and we did not use pruning at the time, because we believe that like the network itself is already optimized. So there is a little chance of pruning. We just assume. That is why actually we did not apply filter pruning. And because we could not retrain the networks for limited amount of time, because only we were given 3 months to get some results, to produce some results. And finally, we consider energy aspects, because the score also consider energy. So, okay, let me explain one by one. So, hardware platforms. At that time, NVIDIA Jackson TX2 was the most powerful platforms. So in fact, actually, we consider several other embedded platforms, including the smartphones and other platforms. Then we found out that still Jackson TX2 is the most powerful platforms at the time. And also, then NVIDIA provide CUDNN, CUDNN, also software libraries. So we decided to use Jackson TX2. And we examine several candidate networks. Since real-time constraint is really important, we first consider the frame per second performance. It's actually the required performance is 33.3 frame per second in Jackson TX2. But when we run the existing network models like LoV2 and TinyLO and VGJ based SSD shot detector, then this is the observed frame per performance. And so this estimated MAP is that like, so if the speed is slow, then estimated MAP is decreases because actually we could not finish this a given number of images. So at the time we could not know how much speed up can be obtained by software optimizations. So pessimistically, we think that, okay, let's try to use, we use TinyLO because it is fastest. And if we obtain twice speed up, then we can meet the time requirement. Okay, so TinyLO is very simple networks. It consists of 9 convolution layers and 6 multiple layers and 1 detection layer. Then what we did is that we first profile the performance of each layers. Profile is performance each layers. The detection and after post-processing is very time consuming. And then if we run this whole networks on the applications, then this is kind of like profile. So CPU and pre-processing and post-processing, specifically output part performs NMS, non-maximum suppression layer is performed at the CPU side. Then easy way to improve the performance is to pipeline CPU and GPU. So we first increase the throughput performance by pipelining the CPU and GPU. And after pipelining, we try to balance the utilization of CPU and GPU. So we apply per layer optimizations. So I will explain one by one and minimize the energy consumptions. That is basic rules we use. So by pipelining CPU and GPU, then we can see that we can parallelize CPU execution and parallel GPU executions. CPU for post-processing and NMS, and GPU for computations of convolution layers. So performance improved is about twice already, 1.77 times. And we found out that GPU is the bottleneck. So now GPU, after pipelining, we found out that GPU is the bottleneck. So what we did is that we apply Tucker decompositions. As I said earlier, so we reduce the computation cost of each convolution. Specifically, the channel is large. And so how many channels to use for input and output channels is also a research topic, but at that time, we just empirically determined that, okay, let's reduce the channel size by half. It will give you 40% improvement. So we apply Tucker decomposition for each layer. As you can see, this convolution 6 and convolution 7, that has the largest number of channels, the gain is most. So we obtain huge gain for convolution 6 and convolution 4. But conversion 1 and conversion 2, so we actually lose, we'll lose the time. So because number of channels is too small, then we don't get any gain by using Tucker decompositions. So we apply Tucker decomposition selectively for the layers that we get gains. Then after applying Tucker decompositions, then we observe that CPU becomes the bottleneck. CPU becomes the bottleneck. Then reducing the GPU is not beneficial to improve the throughput performance. Then the natural way is to reduce the CPU time by parallelized NMS routines. So since Jackson TX2 has a multi-core CPU, so we use OpenMP library. So OpenMP library to parallelize these NMS computations by reducing the CPU time. Then, as you can see this diagram, then GPU becomes the bottleneck again. So the next technique we apply is to quantize. We use floating point 16-bit. So previously we use floating point 32-bit by default. Jackson TX2 library actually support both FP32 and FP16, and the code itself, the reference code, we got used floating point 32. So we modify the code to use half precision FP16. Then we had to modify several parts of the code. Okay, and in CUDNN case, we actually had to change the function signature, and we have to pass arguments with converted types. Okay, and then after quantizations, as you can see, then the later layers, so later layers get gain by using floating point 16, but the early layers, they have precision did not help. I mean, the performance decreased if we use half precision. So actually we did not know why. So we reported this behavior to the NVIDIA. So our guess is that like some floating point, the 32-bit per floating point is assumes in NVIDIA software optimization, but not half point, not half floating point. So actually when we examine, the memory space is reduced by half, and all behaviors are observed as expected. But weirdly, if we use half floating point 16 format, then CPU became idle for unexpectedly long time. We don't know why, but that is the hidden from software library when we profile the execution time of software library of NVIDIA for 14.32 and 14.16. Then that execution time, profile execution time is long for specific APIs. So that is what we reported NVIDIA as a bug. Anyhow, so starting from 17.4 frame per second performance, so after selective quantization is applied, then we achieved sufficient real-time performance. So 3.5 times. The total gain is 2.5 times. So actually we have 2 minutes and 20 seconds slack time. So our next step is to reduce the frequencies to minimize energy. So the original CPU frequency is 2 gigahertz and 2 gigahertz and GPU frequency is 1.3 gigahertz. Then we reduced the GPU frequency and CPU frequency to achieve the real-time constraints. By doing so, we can reduce the energy by 10%. That is what we did. So it took us only 3 months, starting from starting, and actually we select networks and select hardware platforms, apply each technique one by one, and then we could win these competitions. Then 1 year after, the problem was the same, but they actually divide the tracks. So the second track is to use the same NVIDIA TX2 platforms, same as before in the previous years. And at that time, they actually fix some AI framework using Kafka 2. Okay, so we won the first prize in the track 2 by improving the performance by more than twice. How? So the main goal, our main technique is that we changed networks. So in previous years, we used tiny YOLO, but in year 2018, we aim to increase the accuracy by using better networks, YOLO V2. Actually, we examine more networks. So this is which network model, the hardware platform is given. Now we have to determine which network model to use. Here is a candidate we examined. We examined RetinaNet and the fast RCNN and SSD YOLO V3. These are all recent networks and give you higher accuracy. But right over here. So YOLO, so SSD, and RetinaNet, and we actually compare these two. And so because speed matters, the fast RCNN gives higher accuracy, but the performance is too slow. So actually we gave up. So and this measures this data was obtained in a server with Titanex, not Jackson TX2, Also, what we did is that we run those networks. We run those networks on the Jackson TX2 after software optimizations, and compare it. So since 1 year is long time, so we actually compare those networks. But as you can see, so our target latency, target real-time performance is 33. So that belongs to that one. Then as you can see that YOLO V3 actually lose significant energy accuracy loss to meet this real-time performance. On the other hand, YOLO V2 outperforms all other candidates. That is why we decided to use YOLO V2. even though tiny YOLO is fastest, then accuracy is significantly lower than the other networks. So we gave up tiny YOLO. Instead, you use tall YOLO v2. So actually, it tells that choosing the right network is quite important. And also, there are different tendency of some accuracy and performance trade-off. Okay, this is another experimental results within COCO dataset for small objects and medium objects and large objects for so if you look at this diagram at the 33 frame per second data, still this YOLO v2 is superior to other candidates. So this is the techniques, previous optimization techniques we borrowed from the previous years. So we pipeline the networks, we apply Tucker decompositions, and we use half precisions. So we obtain a similar amount of speed up there, but we, similar amount still not sufficient, not close to 33, right? We have to improve more. So we apply merge batch normalizations, and we actually increase the batch size, and we finally reduce the input size, image size. So to image size to meet the floating frame per second FPS performance. So starting from the original YOLO, so by reducing the image size, then we obtained 9 times improvement in FPS performance, and then we lose some accuracy from the original YOLO, but that accuracy loss is outweighed by gain of real-time performance and energy savings. So batch normalization layer can be merged with convolution layer by moving scale part, and by adding bias after convolutions. Then normalization is a linear transformations. Then it can be merged with scale and bias computations. So we obtained 16.2% speed up, and this is a critical step. I mean, so still the real-time performance is not sufficient. Then very effective way is to reduce the size. So input 416 times 416 gives MAP is 49.4. But if we decrease the feature size, then accuracy drop occurs. And as you can see, then accuracy drop is significant if the input size is too small. But here we try to maintain this accuracy loss within 5% or like less than 10%. So that is why actually we decide to use 2.56 times 2.56 to input size. So in the competition, actually we brought these two versions, and take part in that competitions. So wrap up of our design methodology. For embedded machine learning, joint optimization of speed, energy, and accuracy is needed. So our methodology the first step is to choose the right network and right hardware platforms, considering the trade-off between speed and accuracy. Okay, then we apply software optimization methods systematically. So we apply pipelining first, and we apply Tucker decompositions. We applied quantizations and multi-threading in the CPU side, and layer merging, input size reductions, and CPU GPU frequency adjustment. Okay. After that, we new AI platforms appeared into the market. Like Jackson TX2 is not the most effective one. So Jackson Xavier, AGX Xavier board appeared to the market. The recent board is Jackson Orin board, right? Then we continue these optimizations further by using new boards. Like as you can see these diagrams. So NVIDIA increased the AI performance, platform performance by adding DLA, NPUs, neural processing units, as well increasing the number of cores. So NVIDIA Xavier, Jackson AGX Xavier board here, so 8-core CPU, 512-core GPU, and plus 2 DLAs, deep learning accelerators. That is the realization of NVDLA. So, and so we applied the software optimizations for AGX Xavier here. And NVIDIA provides TensorRT as a software SDK, software development kit for deep learning inference. So this TensorRT optimizations perform some compiler optimizations like layer fusing and precision support and kernel auto tunings. And so this is compiler optimizations. So the vendor provided. We actually need to exploit that chance of optimizations. And for given networks, they apply optimization techniques, and they save the optimization engines, and at TensorRT runtime actually load this engine to the board and run. That is the flow of TensorRT, NVIDIA SDK for the Jackson AGX Xavier board. Okay. So my point is that we need to understand hardware platforms and the software SDK and the characteristics and limitations of that. And so, for example, some YOLO V2, they actually use liquid ReLU, but liquid ReLU is not supported in GPU and DLA of the hardware. So we had to replace this liquid ReLU with ReLU and retrain the networks, for example. And also TensorRT supports 4.2.16 and into 8. Or then we try to use which one to use. And also into 8, if we want to use into 8, we need calibrations to reduce the accuracy loss. So we have to perform those kind of like quantizations to use TensorRT. GPU, we used FP16, but DLAs, then we had to use int 8. Okay. So the pre-processing and post-processing are done on CPU, and that inference body itself will be run on GPU and DLA. And so CPU and GPU, we need to transfer the data. The default method is CUDA memcopy, to move data from the host device. And CUDA memcopy, if you are aware of CUDA programming, then CUDA memcopy is used to transfer the data between two processing elements. That is the basic step. Okay, so this is the sequential process of we run this YOLO v2 or any networks on Jackson Javier board using TensorRT. Then this process is done sequentially, but you know, this is not good because we can improve the throughput by pipelining, right? So thread A can be run before thread B, so we can increase the throughput. But this is the default implementation, default baseline. So we want to improve the performance further by exploiting the hardware characteristics. So if we add one more thread, so while processing one image, we can processing the second image concurrently by adding more thread, and here are two buffers. So we add buffers between CPU and GPU, then while the inference is done using the one buffer, and thread put the next image on the second buffer, and we switch these buffers one by one. So we use multiple buffers between threads. By doing so, then we can improve the performance. Okay, and then GPU and DLA have many processing elements inside, and they can execute multiple kernels, multiple execution units. They actually run multiple kernels simultaneously. Okay, so by doing so, to exploit that possibilities, then actually we run multiple execution contexts. So we actually processing two images at the same time by running two execution contexts concurrently. Okay, and then by running multiple contexts, now two threads is running multiple execution contexts are running concurrently, and instead of using CUDA memcopy, then we actually improve the communication. We reduce communication overhead by using shared memory and using different APIs. So we change the APIs from memcopy to the other APIs for zero copy by sharing the memory between GPU and CPU. So now instead of sending the data, we just write the data to the buffer by zero copy APIs. That can be done anytime, anyhow. So we apply that one, and you know, we can parallelize post-processing like NMS. So actually we improve the CPU performance by providing multiple threading, or provide multiple threads. So CPU has multiple, since CPU has multiple cores, we can increase the thread. So our point is that how many threads and how many buffers are used that is another option we can exploit. I mean, so increase the parallel performance, parallel executions. And so we can actually increase the threads of the CPU part. So processing this input, multiple inputs simultaneously. And this is the key techniques we actually developed, that is pipeline the network and using DLAs and GPUs at the same time. So in previously, in all this pipeline diagram, excision context means inference of one image. Inference, but in this, if we actually use pipeline these networks and map this network into DLA and the remaining part is GPU, then we can improve the throughput performance. And if you draw this pipeline diagram, then this inference stage is cut by half by DLA and GPU, and we can improve the throughput performance twice at maximum. Ideally, we can. Then the key issue is that how to pipeline the network. Also, how to pipeline the network. So our CPU, DLA, GPU, or in this diagram, since there are two DLAs, so we can pipeline the inference into 3 stages: DLA 0, DLA 1, and GPU. Then we can improve the throughput performance further, right? Ideally 1.5 times than 2-stage pipelining. So that is a theoretical, I mean, gain by using 3-stage pipelining. Okay, and surely the pipeline network performance depends on the slowest stage. So longest stage among 5 stages determine the throughput performance. And the interesting thing is that, like GPU is more powerful than DLA. And DLA is MPUs or CNN accelerators, but its performance is lower than the GPU. GPU has 512 cores, and DLA is slower than the GPU, but it is more energy efficient. So if you use DLA, we can save energy, but the performance is slower than the GPU. So we found out another options. What is that? We use 2 DLAs to handle 2 different images, and we use single GPU. So GPU. So here, each DLA has its own execution context, but GPU have 2 execution contexts to utilize the GPU hardware resources more efficiently. So this is called partial network duplications. It means that, so we duplicate the first part into one DLA and the other DLA, but we use the same part and just invoke 2 execution contexts for GPUs. So partial duplications says compare with this diagram. Single image thread A1 DLA, single inference consists of 3 stages, but in this diagram, single image consists of 2 stages, but actually two images share two DLAs, one GPUs, and use different DLAs. Okay. So also we actually, if we increase the input threads, and then we can perform batch executions. We actually put more threads and put more execution context because GPU use hardware multi-threading. So if it is delayed by memory access, then we can switch to execute another kernels by increasing the utilizations. So starting from base GPU implementations of YOLO V2, so image size of 416 times 416. So by merging all these together, pipelining, multi-threading, and like partial duplications and batch processing, and we could achieve about 9 times performance without touching the image size. Without touching image size, in Jackson Xavier board, on the Jackson Xavier board, this is baseline execution of YOLO V2. Then without any accuracy loss, we can obtain drastic improvement of throughput. The key is that utilizing hardware resources maximally. So we actually make this process, we automate this process by making, we actually develop some kind of design environment. So we actually explore this number of buffers, number of threads, and number of execution contexts, and network pipeline, where to pipeline, how many pipeline stages, and we have to decide this one. So let's make a framework to set all the above parameters. So that is JEDI framework that is publicly available. So you can download the JEDI framework from the GitHub, and you can try to use it. You could use it. You can use it. So it supports Jackson-Aware embedded deep learning inference frameworks. So it provides options to apply parallelization parameters. It supports both 16 floating point and integer 8 precisions. It is open to public. So here is a configuration. There is a configuration files you can change. So optimization configurations, network configurations you can make. So the key technique involved in this JEDI framework is to decide pipeline decisions, number of pipeline stage, and where to pipeline. So these two factors, these two decisions should be made, and design space is huge. So how can you find the best option combinations to speed up the application? That is what JEDI do for you. Actually, JEDI does for you, and JEDI actually automate that one. So we can pipeline the inference into 3 stages, for example, or 2 stages. And then the number of possibilities is huge, because if the number of layers is large, like more than 100 layers, then this combination is like some increases. And so we explore like these 7 mapping options. So after pipeline the networks, then we map these pipeline stages to where. So DLA GPU, GPU DLA GPU, DLA DLA GPU. So we actually define this, we explore the 7 pipeline, 7 options of mapping of the pipeline stage to that one. So since this find out pipeline stage cut point, the design space is huge. Actually, we implement heuristics in JEDI frameworks. So global search heuristics is that we actually sample the pipeline, these stages, and we actually explore the samples only, sample the stages only. So, and after determine these pipeline stages for the sampled cut points, then we actually explore the nearby stages, nearby connections by local search. So we move cut points greedily around the found cut point in the sampled space. So this is one technique. We first consider like any evolutionary techniques, some AI techniques. We sample the whole design space, and after finding a good samples, then we search the nearby samples. So by doing so, then actually this is benchmark applications, and here this bottom graph shows that shows which option is best. So as you can see, then in most benchmark applications, option PND minus A. PND minus A means a partial network duplication A. So if you look at here, PNDA is 2 DLAs in GPU. Very simple partial duplication for each network. Then we pipeline the inference into 2 DLA in GPU, and we process 2 images at the same time. So as you can see, that is the end results. And here it shows that how many buffers and how many streams, and so how many threads and how many where to cut the networks. That this information is given here, and this results is published in the journal, ACM text journals. Okay. So last one I will briefly introduce you is that, like, so we have to learn multiple CNNs at the same time for same hardware platforms. For example, self-driving car or smart robots. Then we actually use multiple cameras and detect the object from the multiple directions. That is one option. And then also we may have different scenarios. When car is moving forward, then the forward camera is more important. If car is stops somewhere, then actually we may want to examine 4 applications at the same time. Similarly, depending on the car speed, then we have different deadline constraints. So that kind of variations can be specified by kind of finite state machines style, not exact finite state machine. There is kind of state transition graph defining some scenario change. Then we actually consider multiple applications together. Here, this problem is so far, we just assume that one application is running on a hardware platforms. Now we are focusing on, we are dealing with multiple applications running together. Okay. And also the application have different maybe real-time constraints or that one. So we obtained how to map these multiple applications. Then so the details I will not explain fully, but the idea is that so in the previous part, we know how to pipeline the network into DLA or GPU, right? So here this the network is pipeline, CPU, DLA, GPU, and post-processing CPU again. So for each layer, for each applications, we determine this type of pipeline decisions. So the proposed methodology consists of 3 steps. The first one is that for each applications, we find the Pareto optimal mapping solution. Pareto optimal means that the throughput performance versus some resource usages, or energy and power and accuracy. So energy and performance. So that kind of Pareto optimal mapping solutions is obtained at the first step. And second step, actually we find out combination of Pareto optimal solutions. We find the combination of Pareto optimal solutions. And the last step is tuning frequencies. Doing so, actually, in each stage, we use genetic algorithms. So time is already up, so I'm almost done. But so if you are interested in, then you may look at our journal paper to explain that one. So finding a Pareto optimal mapping, we use genetic algorithm to find out the where to pipeline the networks and how to merge these Pareto optimal solutions. We use genetic algorithm again. So which Pareto optimal solutions to use for each applications. And after doing so, then we tuning the frequency to meet the real-time performance. So we have some experiments with 2 different combinations of networks, running the same networks for 4 different input images, or so we use different networks with different complexity of networks and running simultaneously. And then we propose our genetic algorithm based one. And another comparison target is to always run 4 networks always when we make pipeline decisions, when we make mapping, or then we assume that all applications run concurrently. That is global, and that is local. Or local is impractical, infeasible solutions that we actually move task migrations dynamically at runtime. Then our proposed solution achieve the same performance of the local unrealistic performance, but it is much better than global solutions. Okay. So in this lecture, in the first part, I review the well-known software optimization techniques, quantization, pruning, and low-rank approximations. But in the second part, I explain our experience, how to apply those techniques one by one and in systematic way. Specifically, I emphasize that this pipelining and parallelization is really effective method to utilize hardware resources to improve the performance of software. So before applying software optimization techniques, then we first consider this kind of parallelization techniques first. And after determining the pipeline parallelization techniques, and then we actually use software optimization technique to reduce the stage time. If GPU is or DLA or some CPU or whatever processing element is a performance bottleneck, then we actually apply software optimization techniques, approximation techniques to improve the performance of that stage. Then if you look at our papers, then importance of understanding SDK and not SKT, SDK and hardware platform, that is important. Okay, this is the end of my lecture.
Thank you,
I'm so-
Professor, for the great session. Any questions from the audience? Okay. If not, I have one small question,
Yeah,
Professor. So, people nowadays are talking a lot about transformer, and we
Yeah.
all know that this transformer-based network is quite different from this conventional
Yeah, CNN-based
convolutional neural
networks, right?
network, right? So, can you comment on that? How would your methodology will change in response to this, shift to
Yeah,
transformer?
yeah, good questions. And also I mentioned I gave some comments on that. Like the methodology itself remain the same. So we first try to parallelize the transformer networks first. So there are various parallelization options of the transformer networks. It's like we can parallelize matrix complications, or we can the transformer-based networks involve many matrix multiplications that can be parallelly performed. Then we can parallelize the matrix multiplication, or we can parallelize the matrix multiplication itself, or we can pipeline the stages. So we have to determine what types of parallelization opportunities we can exploit. After that, then the key issue is that balance the stage, parallelization staging. That about transformer case, the quantization is really challenging. We actually did some experiments. Then this quantization, 14.16 bit, I think that is really like marginal precisions we can use without accuracy loss. But pruning is different story. So transformer-based networks, there are good opportunities for applying pruning to reduce the time complexity. But anyhow, a transformer-based network is the bottleneck at the memory transfer. I mean, arithmetic intensity is so low, so there is a little chance of data reuse of transformer if the network is large. So I think MPU or transformer accelerator, the chance of transformer accelerator is not high, in my personal opinion. So I'm actually waiting for some PIM, for LPDDR PIM, I think for embed machine learning, embed acceleration for transformer-based networks. I think that might give us some chance about further optimizations.
Got it. Thank you.
Okay.
Any other questions from the audience? Okay, if not, then that's it for the session. Thank you again for the great education session. And the video will be uploaded to YouTube. So yeah, if you need an access to this file, just let me know. I will get you the file as soon as I get download this file from Zoom. So just let me know if you need the file.
Okay, thank you, Professor Yang, for your organizations.
Yeah, thank you. Thank you so much. That's it
Okay.
for the session.
Okay,
Bye.
bye everyone.
See you around.
See you around.